Hi, it's Moser with a quick tutorial on international? No. Intermolecular forces! So, after you've watched this video, you should be able to describe and rank by strength the intermolecular forces that we find. You should also be able to explain the macro-level indicators of these forces. You need to already know what molecules are, and I'm pretty sure you do. So, just like an interstate highway takes you from one state to another, and an international flight takes you from one country to another, intermolecular forces are the forces of attraction between molecules. Okay. Well, there are three kinds of intermolecular forces that we're going to discuss: dipole-dipole bonds, hydrogen bonds, and London dispersion forces. The dipole-dipole bonds are the strongest. Hydrogen bonds come in next, and London dispersion forces, well, they're pretty darn weak, actually. Let's talk about dipoles. You know that the prefix di means two, and we've talked about polar covalent bonds. A polar covalent bond creates a polar molecule. That's a molecule that has a region of partial charge. That's shown with this weird, funky little Greek letter and a plus or minus sign, a positive or negative sign. So, these little regions of partial charge act as poles, just like the poles of a magnet or the poles of the planet, on the molecule. Ammonia, good old household ammonia, NH3, which you've drawn and you've built and you've thought about plenty of times, is one of these molecules. It is a polar molecule. So each molecule has a region of partial positive charge and a region of partial negative charge. Well, a dipole, two poles, di meaning two, is what we get when we have equal magnitude charges which are opposite in sign, which are a short distance apart. This is like magnetic attraction. This is like the forces that we find in ionic compounds, though not nearly so strong. Dipole-dipole forces happen between polar molecules. So there are little bits of attraction as these things are all sort of floating around and moving freely, which they are. I mean, this is a liquid after all. As they move around, there are these little glimpses of attraction between positive and negative ends, and they're not locked into place. It's not like that, but as they move, there are these forces of attraction between molecules. They only act from one molecule to the one right next door. They don't act throughout the entire matrix, but they do cause some changes that we can observe at the macro level. When we take a polar molecule and we attempt to vaporize it, in other words, we add heat until it goes from a liquid to a vapor, to a gaseous state, we're hitting its boiling point. In polar compounds, because of those forces of attraction between molecules, boiling points tend to be higher than we would expect otherwise. Remember, when something boils, it goes from those little molecules being pretty locked together, moving past one another freely, but being pretty close together, to being very spread out, very dispersed, and very high energy. To do that, you have to overcome any forces of attraction that exist between the molecules. And in polar compounds, those forces are a little higher than we might expect otherwise. Let's talk about our second category of intermolecular forces. That would be hydrogen bonds. As you might expect, hydrogen's involved. So, hydrogen bonding happens when we have a hydrogen atom that's bonded to something very electronegative. Typically, we see hydrogen bonds form between hydrogen and things like adjacent oxygens or hydrogen and adjacent nitrogens, things that are pretty electronegative. Can also happen with hydrogen and an adjacent fluorine. So, in a hydrogen bond, as we zoom into this water, every little water molecule has a region of partial positive and a region of partial negative charge. And though those forces of attraction are still only in the molecules that are immediately adjacent to one another, as these forces don't extend through the whole substance. When we attempt to boil compounds that exhibit hydrogen bonding, we see higher than we would normally expect boiling points. It's one good way to test and see if something is showing evidence of hydrogen bonds or dipole-dipole attraction. This is actually what causes surface tension. The hydrogen bonds in the surface of the water form sort of a skin as each water molecule is attracted to the water molecules near it. The surface tension is what allows things like water striders to walk on the surface. And again, hydrogen bonding, just like dipole-dipole attractions, significantly increases boiling point. Our third category of intermolecular forces are the London dispersion forces. And it's important to note that these are pretty weak. They're forces that exist between non-polar molecules and even, occasionally, noble gases. What? Noble gases are so far above all that stuff. I don't believe what you're saying. Well, what we have to remember is that electrons are in constant motion in the electron cloud around the nucleus of any atom, bonded or not. So, as these molecules are circulating, and this is methane, of course, which you've drawn and you've built and we've talked about, as these molecules are circulating, is it possible that a bunch of them end up all on one side of a compound all at once? Yeah, it is. Is it likely? Not really. Does it happen? Yes, it does. When that happens, we end up with sort of a region, instantaneous, momentary, a millionth of a second, but a region, for a moment, of partial negative charge and a region of partial positive charge. It's what's called an instantaneous dipole. In that little tiny fraction of a second, a thousandth or a millionth or whatever it is, there's a momentary force of attraction between the negative end of another molecule, perhaps also experiencing an instantaneous dipole moment. I'm having a dipole moment. Do you mind? This can even happen with noble gases. Here we've got some little xenon atoms just minding their own business, not attracted to anyone, very stable, full S&P on the uppermost occupied main energy level. You knew that. There can come a moment, however, where two of these atoms have a simultaneous little whoo-hoo instant dipole moment. Well, hello, cutie pie. Mwah! But it passes pretty fast. The minute the electrons return to a more even distribution, the attraction is over. The moment has passed. It's not going to go anywhere. London dispersion forces don't really do anything to change boiling point, heat of vaporization, any of those things, but they do happen, and so you should be aware of them. Okay, can you briefly describe and rank by strength intermolecular forces? Can you explain the macro level indicator that's the best way to gauge these forces? That'd be boiling point. If you do, that's it. You're done. Get going.